This video is going to be on Unit 6.1, Shapes and Molecules of Ions. So the first thing which really lays the foundation for progressing in this topic, you need to know what VSEPR theory is. And all that stands for is valence shell electron pair repulsion theory. But you can just think of it as VSEPR. You don't really need to know what it means. But basically, this is saying to us that pairs of electrons will repel each other as far away as possible. So imagine if you have two magnets with their like poles, they're going to push each other away. The same thing, the electrons are negatively charged, so two of them are going to push each other away, and it's going to be as far away as possible. It also states that due to electrons wanting to push each other away from each other as far as possible and evenly, this is going to determine the shape of a molecule. The next one that we need to know is that lone pairs of electrons will repel stronger than bonded pairs. And the last one that we need to know is that each lone pair of electrons will offset the angle of the bond by about 2.5 degrees. And that's all that we really need to know about that. The next thing that we need to know is the different types of structures that molecules can have. And there's 4 of them. So there's linear, which looks like this. So there's one central atom and then 2 coming off of it. As you can see, it's a line, hence linear. Then there's going to be trigonal planar. It's a bit of a weird word, but this one is when there's a central atom and then coming off in like triangle, hence trigonal, there's 3 other atoms coming off of it. And the angle here is going to be 120 degrees. And this one here is going to be 180. So the bonding angle here, 180. The bonding angle here is 120. Then there's tetrahedral or pyramid. Which looks like this. So there's the central atom, then there's one coming off of it at the top, one coming off to the side, and then 2 more coming off to the side. We're going to talk about these symbols in a second. And we need to know that each bonding angle here is going to be 109.5 degrees. And the last one that we need to know is going to be octahedral. And this one, there's going to be a central atom, there's going to be one coming from the top, one coming from the bottom, then there's going to be one here, one here, one there, and one there. And we need to know that the bonding angle here is going to be 90 degrees, so 90 degrees. And these are the only ones that there are. But for linear, there can be non-linear, which it still falls into the same group as linear, but it looks more like this. And this happens when there's a lone pair of electrons at the top. And as said here, lone pairs will repel more than bonded pairs, so they're going to push this down. And a molecule that you can think of is like this is water, and we're going to get to that soon. So the symbols, just a line like here, or this double bond here, this just means it's on the plane. So you can think of it as if this pen here is an atom, it's going to be the position of the atom that's connected by a line is going to be on the same plane of the pen. So it's going to be here, if the central atom is there. The second one that we need to know is this one here. And this one means it comes out of the plane. So if you imagine, we have this here, and then coming out of it is going to be like this, because these are 3D structures. So it's going to come out of it like this. And then the other one This one, that means it comes out, but it goes behind. So if we look at it like this, it's going to be going behind it. So it comes out from the back. And then I'll put here, it comes out of the plane from the front. So that's what these symbols here mean. Alright, so the next thing that we need to know is this. So a bonded pair with a bonded pair is going to have less propulsion than a bonded pair with a lone pair, and that's going to have less propulsion than a lone pair and a lone pair. So you can think back to this again. Lone pairs of electrons will repel each other as far as possible. So the lone pair and the lone pair is going to repel as much, the most out of all of them. Then the bonded pair and the lone pair, that's still going to repel, but it's going to be a bit less because it's only got one lone pair. And a bonded pair and a bonded pair, that's going to be, it's still going to repel, but it's going to be the smallest out of all of these. So I can just write, maybe use a different pen. Now we're going to look at some examples. So let's say barium fluoride, which is going to have the formula BF3. So if we draw its covalent dot cross diagram, we're going to have a B in the middle for barium. Then we're going to have 3 F's around it. And we know that this is going to have three single bonds, sorry. So the barium is in group, if we get a periodic table, we can see that barium is in group, boron is in group 3. So it's going to have 3 electrons missing from the outer shell, so it needs to gain 3. And fluorine is in group 7, so it's got 1 electron missing and it needs to gain 1. So that means that the boron is going to take 1 electron from each fluorine, and then fluorine is going to take 1 per atom. The fluorine is going to take 1 electron from the boron. So if we just finish this diagram, and I find that these diagrams are really helpful in trying to get the 3D structure because it makes it a lot more clear. So we can see that there's a bond here, here, and here. And we can also see that there's 3 of them. So if we draw it, then we're going to have a B in the middle. We're going to have a single bond connecting to an F. We're going to have a single bond connecting to another F, and another single bond connecting to another F. And from this, we can see that this is a trigonal planar one. So we can see that this angle here is going to be 120 degrees per angle. You can think of that as 360 being the whole circle, divided by 3 is going to give 120 degrees. But that only really works for this one. When it gets into the different dimensions, this doesn't really work anymore. But it works for linear and trigonal planar. So the second example that we're going to do is methane. So if we have CH4, which you should know is methane, there's going to be a carbon in the middle, there's going to be a hydrogen on top, a hydrogen to the side, a hydrogen underneath, and a hydrogen to the other side. We know that carbon is in group 4, as we can see on the periodic table, and hydrogen is in group 1. So this has a charge, this has 1 plus electron that it wants to give away, and then carbon has 4 that it needs to gain. So we can just draw it like this. So to get an outer shell, hydrogen needs to gain 1 electron, so it's taking 1 electron per hydrogen atom from the carbon, and carbon needs 4 electrons, and it takes 1 electron, and it takes 1 electron from, or shares 1 electron from each hydrogen. So if we was to look at this, we know that there's 4 hydrogens and they all have single bonds. So we can't use the trigonal because this is 3. So we're gonna have to use tetrahedral because you see there's 1, 2, 3, 4 around the central atom. So we can put a carbon in the middle, we can put a hydrogen on top, a hydrogen to the side, a hydrogen coming out, and a hydrogen going behind. And you can think of this as kind of like this shape, if that makes any sense. So you have your carbon in the middle, your hydrogen at the top, your hydrogen at the side, and then your other 2 hydrogens coming out from the front and the back. The next one that we'll do is sulfur fluoride, so SF6. So this one, if we draw the covalent bonding dot cross diagram, we'll have a sulfur in the middle, and then we'll have 6 fluorines around it. Now looking at our periodic table, we know that fluorine is in group 7, so it needs to gain 1 electron in its outer shell for it to be stable. And we know that sulfur is going to be in group 6. But this disturbs the octet rule in the fact that it's not going to have 8 electrons, it's going to have 12, but we'll get to that. So we know that fluorine needs to get 1 electron from it. So we can put XO, 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 XO. And then we can just fill in the rest of the fluorine. So put in 6 more, because fluorine originally has 6 electrons, 1, 2, 3, 4, 5, 6, 7 electrons, sorry, and then it gains 1 from the sulfur to make it a full outer shell. Alright, now if we look at this, we can see that 6 atoms are surrounding the central atom. So this is going to be the octahedral one. I don't know why it's called octahedral. Octahedral would imply 8, but I don't know. That's what it is, isn't it? So we can say our sulfur is in the middle. Then we have a fluorine coming from the top, a fluorine coming from the bottom, 2 fluorines coming out from the front, and 2 fluorines coming out from the back. And we know that the bonding angle here is going to be 90 degrees. So one that we're going to look at now is going to be water. So this one is a bit weird in the sense that it's got 2 lone pairs of electrons and 2 bonds. So if we draw the dot cross diagram for water, we're going to have 2 hydrogens and 1 oxygen, and we're going to have 2 lone pairs here, and then it's going to have a single bond for each hydrogen. And this is because hydrogen has 1 electron in its outer shell, so it needs to gain 1. And oxygen has 6 electrons, so it needs to get 2. So 1, 2, 3, 4, 5, 6, and then it's getting 2 from the hydrogen. So this one, if we was to draw it, we would have an O for oxygen, then we would have our 2 lone pairs, and then we would have our hydrogens coming out here. But this bonding angle, this is another one that we need to know. As said here, each lone pair will reduce the bond angle by 2.5. So we can think of this as kind of like a tetrahedral because it's got 1, 2, 3, 4 coming from it. If you look, 1, 2, 3, 4. So we can say there's 2 lone pairs and there's 2 bonds. So there's a total of 4 things happening. There's 1, 2, 3, 4. So that's why we say it's kind of like tetrahedral. And we know that a tetrahedral bond, so tetrahedral bond angle, is going to be 109.5 degrees. And we also know that each lone pair will reduce the bond angle by 2.5. And we see that there's 2 lone pairs. So we can say that the bond angle is going to be 109.5 take away 2 times 2.5. And obviously that's going to give us 104.5 degrees. So this bond angle will be 104.5 degrees. The next one that we're going to do, and the last one, is going to be carbon dioxide. So we see CO2. So if we draw this, we're going to have C, we're going to have O, and we're going to have another O. And we know that there's going to be 2 double bonds here. And this is going to take up all of the electrons. And we can see that oxygen has 6 electrons in its outer shell. And so 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. So this here, if we was to draw it in its 3D structure, this is going to be what we call linear, because this one is just going to be O, and then, sorry, it's going to be C, and then it's going to have 2 O double bonds. So it's just going to be like that, with a bond angle of 180 degrees.